Good morning, everybody. It's a great pleasure for me to be in China and give a talk about the information revolution, its impact, and the scientific challenges. So this revolution started 70 years ago. You know, the foundations have been set by Alan Turing and Kurt Gödel. We have the first computers in 45, and then things went very fast, very, very fast. You have the convergence between computing and telecommunication, which opened the way to the web, to the information society, and then you have many important landmarks, embedded systems, the result of the convergence between computing and physical systems, multi-core systems, cloud computing, and an important landmark I'm going to talk about is the Internet of Things. So things are evolving very, very fast, and it's hard to say what will be the digital future in, say, even 10 years from now. We have devices, embedded systems everywhere. We have today more than 1 trillion of devices deployed over the planet, and each device delivers some services. The dream is how to integrate all these services and provide global services. So what is important also to notice is that we are having a convergence, a technological convergence, which means that we try to combine different technologies in different sectors. So we would like to have a converged network infrastructure that goes from wireless sensor networks to the internet, and this infrastructure will probably be based on the IP protocol. And then you have integration of devices. You use the same device to make phone calls, to watch TV, to monitor your health, what else, okay? And you have integration of services, of course, and something very important is that also you have convergence of policies. Convergence of policies means that you try to harmonize standards to regulate content and quality of service in order to enable the pervasiveness of technologies. So very important things are happening, and I would like to say that software companies have changed their strategy in order to integrate this. This is IBM's vision for a smarter planet, and you see that, okay, what do they say? That the world is instrumented. You can sense the condition of almost everything, and it is interconnected, which means that people and systems can interact in many different ways. And the most important, the world should be intelligent, which means that intelligence means that you can predict, anticipate events, and optimize resources. Okay, nice, interesting vision. And the other, of course, so big software companies are following this. And if you read the newspapers, you'll see that this year in August, Google acquired the Motorola Mobility, and of course, 1 month later, what happened? Microsoft acquired Nokia. Interesting. And if you read Time magazine of September 14, you will see that there is a long article about the Google universe, as they call it. And here you see that Google is interested in making everything smart. Cars, phones, energy distribution, health, whatever. So this is a very, very ambitious vision. And this ambition has no limits, as you can see. This is the cover of this issue, okay? I let you think about that. Okay, so let me talk about something more serious. This common vision will probably be implemented in what people call the Internet of Things. So this is a Freescale's vision about the Internet of Things. What's the idea? We have so devices everywhere. they are interconnected, and the whole system should be intelligent. And where intelligence comes from the cloud, because the devices send data to the cloud analyzes the data, and helps devices to make decisions, okay, to make decisions about, optimal management of resources, etc. This is very interesting. So let's get a closer look. In the Internet of Things, we'll have smart grids. What means smart grids? You will have smart distribution of energy, because today we have to optimize, to make an optimal use of resources, of sources of energy that have different characteristics. And this is one thing. Smart factories, of course. So fully automated factories that will be remotely controlled. You will send the specifications or a virtual model of a product, and they will produce it and send it ready for use. You will have, of course, smart highways, so highways with sensors that can monitor traffic, weather conditions, and eventually reroute traffic, whatever. Smart vehicles, so you probably seen a Google car. We will have driverless cars in the future, where we will give a destination, the car will bring you to the destination without any intervention. And of course, you will have also whatever, smart vehicle safety. Car manufacturers talk now about active safety. Active safety means that if there is a potential danger, the control system can take over and avoid accidents and things like that. And you will have also telehealth, a remote health monitoring. You take some smart pill that has some chip with the sensors that can measure some health parameters and transmit them to your medical doctor. So this is a very, very interesting vision. And for this vision to come true, you understand that we should have the adequate networking infrastructure that should be safe and secure, and this is not the case yet. So this is an overview of my talk. Okay, so let's move on. I think that now I'm going to talk about technical issues. I would like to make clear the difference between pure software and system. Okay, so a program computes a function, and you see that a program, we have theory for writing programs that are more or less correct. Programs are simple, are simple artifacts. Now, the big difference between a system and a program is that a program computes a function, while a system is composed of hardware and software and continuously interacts with an environment. So if we want to mathematically understand what a system does, it's not just a relation between input and output values, it's a relation between input streams of values and output streams of values. So the mathematical setting is quite different. And I would like to emphasize that systems are non-terminating. Okay, any system is potentially non-terminating. And their behavior is non-predictable, is platform dependent. Why? Because the dynamic characteristics of the interaction between the system and the environment are important, and we have no theory for that. So these are two different words, and this is something I would like to emphasize. And here again, I explain the same idea. What counts is the dynamics between the system and the complex environment they try to control. And this means that we understand the dynamics also of the complex environment. So systems are hard to design. not because of complex data and algorithms, but because they are open, because of you can have very subtle interactions between the system and the environment. Okay. Now, this brings a new trend that breaks with traditional systems engineering. So we're not talking about the technology you have in your lab. You have, for these systems, new technical requirements, for instance, reactivity. Your laptop may not react within some bounded delay to a command, okay? But this is not acceptable for a flight controller. We have very strong autonomy requirements. If you have embedded systems, you cannot have a manual start, okay? And of course, for all mobile devices, we have very strong power autonomy requirements. So you don't program power devices, you don't develop the software as you develop the software of your laptop. And you have dependability requirements. Dependability means resilience to any kind of hazards, and scalability requirements. And of course, as these devices are in mass market products, you have to take into account economic requirements. And as I said, the technological challenge here is to be able to design and develop systems of guaranteed functionality and quality and acceptable costs. And we have almost zero theory for that, or very little theory for that. So let me say a few words about system design. What means design? Design is the process that allows you to build an artifact from given requirements. So the requirements are your desires, okay? You need something. Here you need an apple pie. And so design is the process that leads from your desire, what you wish to have, to an implementation, to a realization. And this involves two main steps, as you see. One first step where you have a recipe, and then a second step where you choose the resources, and this will determine the quality of the pie. So very similarly, when you design a system, you start from requirements. The requirements are declarative, and then you write some application software, and then you try to implement, and then you have the system, okay? So you have these two steps, and these are important gaps because, okay, this is something I'm going to explain, and an important issue here is what is correctness. Correctness means that what you get at the end is compliant to your requirements, okay? And in these two steps, so we distinguish between correctness with respect to functional requirements. So application software should meet functional requirements, and the final system should meet functional and extra-functional requirements. So let me explain how the concept of system correctness differs from the concept of software correctness. So correctness can be characterized by two types of requirements. One type of requirements is trustworthiness. What means trustworthiness? Trustworthiness means that my system will behave correctly despite many different kinds of hazards, okay? Hardware failures, of course. Software design errors, of course. Disturbances from the environment. This is, and of course, malevolent actions. This is the safety issue. But having systems that are trustworthy is not enough. We need also, because you can achieve trustworthiness at very high costs, we have also optimization requirements. And these are quantitative constraints that relate performance to cost and trade-offs between them. I hope you understand this. System users need performance. Performance means how well the system behaves with respect to its potential users. And of course, this should not cost too much. And you are seeking trade-offs between the two. Now, just to make clear the distinction again, between trustworthiness and optimality, Trustworthiness means qualitative correctness. So here you see the system states, the green states are trustworthy, red states are non-trustworthy. While optimization requirements characterize execution sequences, and so you cannot talk about an optimized state. And an important remark, I hope you understand this, is that two types of requirements are often conflicting. Why? Because to achieve trustworthiness, usually you need additional resources, and okay, I hope you understand this. Something I would like to emphasize from the beginning is that there is a significant difference between traditional systems engineering and computing systems engineering. So if you are a civil engineer, you want to build a bridge, well, you have theory, you write down equations, and you know how to build a bridge that with very high probability will not collapse in centuries, okay? Now, for systems engineering, things are different. Why? For many reasons I have no time to discuss. One explanation is that computing is a very young science, okay? But I think the type of theory we'll have for computing will be different from the theories we have in engineering disciplines that are based in classical physics. So the situation today is not, okay, I say that we are in a situation where mechanics in the Middle Ages, so we don't have constructivity results, and this is something I'm going to explain. As I spent a part of my life on verification, I would like to say a few words, because 20 or 30 years ago, we believed that verification would allow us building systems that are correct. And, okay, what means verification? Verification means that a verification method allows to compare a model of the system against requirements. So as the model and the requirements will be analyzed by a program, by a computer, we have to formalize them. And the requirements usually are given to engineers in books written in English or in natural language, should be translated, should be formalized, usually in a logic, and they should be consistent. Consistent means there should be no contradictions, and also they should be complete. Complete means that you don't forget any essential property. And okay, so these are demands about the requirements, and for the model, when you build a system model, it needs to be faithful. Faithful means that any property that holds for the model will hold for the real system. And also, you probably know that verification methods suffer from limitations, complexity limitations. I'm not going to comment on this, but I will say that today systems are not trustworthy, or as trustworthy as we would like them to be. And when you try to build trustworthy systems, then it costs a lot. And this is something important to understand. Now, just to finish with verification, I will say that for requirements, we lack adequate languages for expressing optimization requirements, checking their consistency and completeness. We don't have faithful modeling techniques for systems. For instance, we do not very well understand how the hardware interacts with software. Even if we perfectly understand how our software works, the hardware works, there is still a problem. I don't know how to solve this problem. So, the third is that verification is limited now to small and medium-sized monolithic software and hardware systems. And let me say that a consequence of this situation is that today when we build systems, we distinguish levels of criticality. And the design techniques are very different depending on the level of criticality we are seeking. So we have critical systems, safety or security critical systems. I hope you understand the term. And we have levels of criticality. To the other extreme, we have a best effort system. So what it means, best effort systems? Best effort systems are systems where what is important is some optimization of resources and keep the system availability above some threshold that is acceptable by the user. And then you have mission-critical systems. All the infrastructure is mission-critical, okay? And, okay, now it's important to understand that, for instance, for safety-critical systems, we require the probability of failure that is of the order 10 to the minus 9 failures per hour. And for mission-critical, it's only 10 to the minus 6, okay? So you have 3 orders of magnitude of difference. And another important fact is that each time you try to improve reliability by an order of magnitude, you have to pay a lot, exponentially more, to improve reliability. Okay, so today, you know, because of the fact that we don't have flawless systems, even for critical systems, we are not, okay, we cannot guarantee absolute flawless. You have a lot of failures that are reported and many more failures that are not reported, okay? So the failures here even are for critical systems. You have a lot of problems, for instance, in the use of medical devices, problems with cars, aircraft, okay, power management systems, and of course, banks are losing a lot of money because of cyber attacks. Okay, so this is a slide that explains how, if you want to have very high confident systems, then you have to pay a lot. And this slide shows in an exponential, in a logarithmic scale, the evolution of costs of system development in aerospace industry. So in a horizontal axis, you have the complexity in terms of source of lines of code. So you have exponents of 10. And then you have some logarithmic scale to measure development costs. So you see that while, for instance, in the IC industry, integrated circuit industry, the costs have remained constant despite the exponential increase of the complexity. For aerospace industry and for other also sectors, you have this exponential increase of the cost. And just to say that for systems, trustworthiness costs a lot, and this is another figure that shows that if this trend is confirmed, then to build a single aircraft around 2060, the US defense budget will not suffice. Okay, so if you want, you have strong requirements about trustworthiness, then you have to pay a lot today. And now I will talk about the scientific challenges. The first, I have 3 scientific challenges. The first is, and I hope you understand this, for the new generation of systems that continuously interact with the environment, we have to link physicality with computation. So computing with the physical world, first I would like to say that computing is a discipline in its own right, as physics studies phenomena, transformations of energy or mass, and computing deals with transformations of information. And biology, of course, is another separate discipline. So it's important to understand that information is the other dimension of the reality. And the information is immaterial, okay? It's non-material, okay? I'm talking, you understand something, you take notes, you put this in a book, whatever, okay? Information is immaterial. And computing is a discipline that is independent from computers. Okay, I mean, computers are just instruments, and here I give a quote from Dijkstra. And an important idea to establish bridges between computing and other disciplines is that phenomena can be understood in two different manners. Either through the study of laws, as physics does, so we talk about of conservation of energy, of motion, etc., and also as computational processes, as programs. So, for instance, in biology, we talk about, we can consider as algorithms, transformations of DNA, or, for instance, you can consider all physical processes as computational processes. When I throw a stone, the stone is a computer. It describes a parabola. Okay, so it's a physical computer. Okay. So I like this idea of computational thinking proposed by another keynote speaker who is here, Professor Janet Wing. And the idea is that algorithms and algorithmic problem solving can be applied to other disciplines. And I believe this is a very strong idea in order to bridge the gap between computing and other disciplines. And I like also this quote, the universe is like a parallel computer, it's a space of computation. Now, let me try to be a bit more technical, how we can relate physical systems and computational systems. It's clear that both are dynamic systems, so they can be described by an equation, a state equation, of the form x prime f of xy, where for computing, x prime is the next state. There is an error there. And for physics, x prime is the derivative of x, okay? I hope you understand this. This is very elementary mathematics. The difference being that variables in physics are functions of time. This is an important difference. Now, the important question is whether computing systems can be studied as scientific theories. And let me try to explain the idea. So on the right, on my right, or so, yes, on your right, you have a mass spring system, the differential equation that describes dynamics, and the associated law from which you can derive the equation, okay? So, and on the left, you have a program that computes the GCD between x and y. And you have also a law, okay, that's what we call a loop invariant. So there are some analogies, interesting analogies, but there are also some important differences. What are the differences? The physical system dynamics is parameterized by a parameter, at least in classical physics, by a parameter, it's time. And processes are inherently parallel and governed by uniform laws. So the nice thing about physics is that you have uniformity of laws, which you don't have, unfortunately, for computing. And of course, you have no notion of global time. Okay, now to be more concrete, if I am, say, a systems engineer, I want to design a system. I should understand a lot about programming, software, about the underlying resources of the hardware platform, and you see, okay, what are the resource constraints I may have, and then, of course, about the environment that is perhaps driven by continuous dynamics, but there are also constraints that are such as deadline, jitter, and throughputs, okay, that are related to constraints that are imposed by users. Now, if I want to be a good engineer, I should so understand hardware a bit or a lot. It depends on what I want to do. And of course, I should understand control theory, okay? Theory of dynamical systems and things like that. So I think that system design should coherently integrate all this, and this is also a dream for some researchers like myself to extend computing to integrate methods and paradigms from physical systems engineering and control, and this is okay, something people are working on that. Now, today, in this vision, this vision is materialized somehow by this concept of cyber-physical systems. What are cyber-physical systems? Cyber-physical systems are systems whose components integrate tightly computing elements, communication elements, and control technology. Okay. So in order to study these systems, you need theories that combine continuous dynamics and discrete dynamics. And I hope you understand that these systems are very, very important in overcoming many challenges. Okay, now, what makes possible the emergence of cyber-physical systems today is that it's three things. We have small components, nanoscale, microscale components, such as sensors, actuators, processors. We have advanced in systems engineering, and we have wireless sensor networks. So we have all the ingredients to achieve this. And one dream in cyber physical systems engineering is that we build products, systems, out of cyber physical components. Let me take some time to explain this. So today, you have CAD tools that allow you, when you want to build an object, to give its geometric characteristics, and you have a 3D model. And this 3D model can be given to a 3D printer and produce the object. Now we want to extend this idea. So instead of giving only the geometrical characteristic, give also other characteristics. Give thermal characteristics, resistance of materials, give, specify, say that we will have also processors in the components and things like that. And for this engine, to specify the cyber-physical components and build a virtual model of the engine that we can send to a smart factory and build the engine. So this is for the moment a dream, but I think it can become a reality. Similar things for wings of an aircraft. We would like to have smart wings. Here you see that the wing is composed of tiles, and tiles are cyber-physical systems. And in modern wings, we will have a skin of sensors that, like our skin, that will be sensing different parameters of the flight in order to get better stability and to reduce fuel consumption. Okay, so this is really a dream. People are talking about the third industrial revolution. So the idea is that to extend the concept of 3D printing to very complex systems. Okay, and this slide further explains the idea. So you want to build a virtual prototype of a vehicle. Here you see bottom down and left. And you have to integrate at different scales components that have different characteristics, and this is really a very nice dream I like. Okay, now let's move to the second challenge, that is constructivity. In any engineering discipline, you want to build systems out of complex systems out of components, and you have only a very small number of types of components. So the problem today is that in systems engineering we don't have such a typology of components. People do not agree on a common component model. Even in software engineering, there is no agreement. So we need this, and in addition to that, of course, that's what I call constructivity. That is something that other engineering disciplines have. is that we achieve correctness by construction. So what means correctness by construction? If I have components, so these are bricks, say, and they are smiling, they have some guaranteed property, they meet some property, then I would like to have theory to stick them together and build a composite component that still smiles, so it is still healthy, and I need the rules for this. So today, for instance, for systems, we need compositionality rules to build deadlock-free systems out of deadlock-free components. We don't have theory about that. But this is not enough. You need, in addition, another type of rules I call composability rules. So let me consider again the previous example. I have my bricks. I apply compositionality rules, and I can build a wall. So these guys are smiling, okay? Now, this wall should not be too high. So if I make it too high, some guy may suffer, okay? So I should have theory to understand possible interference of the features of the components. And this is a very, very important problem in systems engineering today. We talk about feature interference in operating systems, middleware, telecommunications. And if we don't, for instance, have composability theory, we will never be able to guarantee some correctness of reconfigurable systems. When I bring a component or modify the structure of the system, okay, I need theory for that. Now, the third and last challenge is intelligence. And this is the most important challenge. Let me try to explain this. And of course, intelligence, when we are talking about intelligence, we connect the concept to human intelligence or natural intelligence. So I think that it's important for us to get inspired from and understand how living organisms work. So let me point out that there are some similarities between computing systems and living organisms, to the extent that computing systems and living organisms use memory. There is this distinction between hardware and software is still pertinent for living organisms, and use languages. But there are also some very remarkable differences. For instance, computational phenomena in living organisms are robust. Robust means that small changes will have, small modifications will have commensurable smaller results or commensurable results. They have a very interesting built-in mechanism for adaptivity and other interesting properties. So I believe that a cross-fertilization between the disciplines is really very, very interesting, and I think we should work towards that. Now, to avoid misunderstandings, I would like to explain that when I'm talking about intelligence, artificial intelligence, this has nothing to do with the vision our community had 20 years ago, and the vision was that human intelligence can be so precisely described that it can be matched by machines. So you've probably seen this. We are using supercomputers to show, for instance, how a supercomputer can beat a chess champion, or we're using supercomputers in TV games. I don't think that these supercomputers exhibit any intelligence. They are dumb. They are doing what they are programmed to do, okay? They are solving heavy computational tasks, but that's it. Okay, now, I'm not talking about that. I think that we should understand, okay, let me say it in a different manner. I think that the Turing machine-based model has some limitations, you know, the theoretical limitations, and cannot match, we cannot understand human intelligence by the standard computational model. I don't have time to explain this. Let me say that in our mind combines two types of thinking, fast thinking and sequential thinking. fast thinking means, okay, fast thinking is unconscious. When, for instance, I play the piano, or I walk, or I speak, okay, I'm thinking, but this is unconscious, fast thinking. So this is a type of thinking we don't understand very well. And computers can simulate somehow the conscious thinking, which is sequential, and to some extent, because humans can make abstractions and can make induction, find induction hypothesis, and this is very hard for computers. So what I would propose is that we study other models of computations that are inspired from biology, and personally I have seen very impressive results in machine learning, image recognition by using neural networks. So this is a direction we should pursue. Now, another concept for intelligence that is very useful in systems engineering is what I call adaptivity. What's the idea of adaptivity? When we design a system, at design time, we cannot foresee all the dangerous situations. So the idea is that we use control-based techniques to ensure correctness despite of the uncertainty, okay? So here I try to explain very briefly this idea. So the system, when you design it, it will not be flawless. You will have hazards, but you assume that you have a very, very smart controller, okay, that monitors the system, the state of the system, detects all this deviation from the nominal behavior, and steer some parameters that mitigate the effect of hazards. So this is, okay, hope you understand the idea, and the question is how we can design some controllers, controllers of this type. I will say that the most general type of controller should work as our mind works. So our mind combines three types of functions in a hierarchical manner. So let me try to explain this by giving an example. So the central function is management of objectives. At some state of your mind, you have different objectives. So you have a model of the external world, you evaluate, and this, okay, you apply some criteria you have in your mind, and you say, well, amongst these three objectives, I choose to go to the stadium. Okay, so in that case, you activate a planning function, and how to go to the stadium. So you go to the stadium, and once you have this experience, then what do? You learn something about that. So you evaluate in your mind, and the learning function, so you learn something. And the learning function will, so if, for instance, you find that it was not a good idea to go to the stadium, then you will modify the parameters of the model that uses your objective manager. Oh, this is a principle that is currently applied in many computing systems, in data mining, in networks, in multimedia systems. But okay, I would like to have a general theory to deal about that. Now I'm very close to the conclusion of my talk. I would like to discuss some very important issues. I hope I explained how important design is becoming today, and I think it's also a very interesting question to see how we can give some scientific foundation to design, and how design is compared to science, where science, by science I mean all the activities we have to understand the world. So science tries to understand the world, we build models of the world, okay, and now we are lucky because ideas and models can be formalized and can be put in computers, okay? And this is the very good news, okay? And even we can experiment ideas today. So we have the other arrow that is design, system design that goes from the ideas, from the heaven to the earth. And I would like the design to have a kind of design science. And okay, I agree. Design formalization raises many hard problems such as formalizing natural language, synthesizing programs from formal specifications, okay, but these are very interesting problems. And it's a pity it has not attracted so far the attention of theoreticians that prefer simple and elegant theories and not multidisciplinary research. Okay, this is something I explained. And of course, this is the important question, whether we can endow design with a rigorous scientific basis. And this is, I think, the important scientific challenge. So this is a huge intellectual challenge, at least for me. And if we fail meeting this challenge, I fear that we will not be able to continue this integration. We will be hitting soon a wall. For instance, the vision I have presented about the Internet of Things is not reachable because the quality of the communication infrastructure is not good enough. So this to finish, and I think there is a difference between the cyber world and the physical world. The physical world has been given to us. The cyber world, we've built it, and it's a matter of responsibility also to ask us to wonder whether we have built the best possible world. And I think that this is not the case, and this is improvable, and that the toughest battles are still in front of us. Thank you for your attention. Thank you.